Okay, so last class you learned about some terms, and the terms were effectively specialized segments that belong in triangles that do something more than we might have expected. And today is going to be the opportunity to extend those further. And unfortunately, this is a day when constructions would be really useful. And I know that many of you went out and purchased one of these cool tools, and I still hope we find a way to do it. But in order to make it available to everybody, this is one of the topics that has been removed from this year is constructions. But today, I think I can use constructions in a way that will make some of this stuff make sense to you. So first thing I want to do is I want to draw myself a triangle. And you do not need to follow along with this. This is just fun information for you to see. Actually, I just missed that a little bit, so I'm going to come over there. All right, so ignore that. This is a triangle. Would you classify this triangle, please? Is it equilateral? Isosceles? Acute? I think it probably is acute. And I think it's probably scalene, but of course I'm guessing. So what I'm going to do is I'm going to construct a couple of segments. And one of them is going to be the thing called a perpendicular bisector. Perpendicular bisector has two words. No, you do not need to copy this. This is just for your information. And it's not even anything that applies. It just gives you some background knowledge about where this stuff comes from. I'll give you the notes that specifically give you what you need. So a perpendicular bisector has two components in the name. It's perpendicular and it's a bisector. And as you know, bisect means to slice in half. So I'm going to set my compass in such a way that I want to find that exact middle point. And the way I do this is I go more than halfway, and I'm going to make a portion of a circle with that. And then I'm going to leave it the same size, and I'm going to go to a different vertex and do it again. And then I'll go to the third vertex, and I'll do it again. And by doing this, what I've built is these three little kind of football-shaped things. And it turns out that if I connect the endpoints of these football-shaped things, I produce a segment. And that segment does two things. It bisects this side, and it is explicitly perpendicular to this side. And because of the way I did this, granted, I did it in a very officious way. If I do it from this one, here's the different football going for this other side. And again, this bisects this segment and is perpendicular. And you'll notice that they meet. Is that significant? Nah, it just means they're not parallel, right? But when I turn this again, and now do my third one, and again, it bisects this side and is perpendicular, but it's a little bit unique. Notice that they all meet at a single point. It's called a point of concurrency. And what it means is that they share a point. Now, is that relevant? Is that interesting? I don't know. What if I told you this was the center of this triangle? What would be your response? Does that look like the center to you?
It doesn't look like the center.
It doesn't look like the center, does it? How many of you would agree? Give me a hand up. It does not look like the center of the triangle. But what does the center of a triangle mean? Well, it's in the middle, okay, but in the middle of what? Turns out, watch this. If I take my compass and I put it on that point we just created, and I see exactly how far away I am from this vertex, and then I draw a circle through that vertex, note that it hits exactly this vertex and exactly that vertex. This is the center of the triangle. It is equidistant from all three corners. So that if you had a triangular plot of grass in your backyard and you wanted to make sure that you got water to every single place, this would be where you'd want to place your sprinkler head so that it reaches the furthest points from the same distance. It is the center of a triangle, but that's not the triangle center you would think about, is it? There's different triangle centers. A different one might be if I were to, this is called the circumcenter. And we'll learn about that today. There's another way I could do it, which is, again, I'll just give myself a triangle to start with. And I'll make it a slightly different looking triangle. How would you classify this triangle now? Does it still look acute? I think it's obtuse now. This is a bigger than 90-degree angle, but we'll see. So now what I'm going to do is I'm going to do, instead of perpendicular bisectors to a side, I'm going to do angle bisectors. And it turns out it's very similar to what I just did, but I have to begin with an arc that is like a reference arc. And then what I'm going to do is from this point of intersection, I'm going to do the same thing I did before. I'm going to go more than halfway and make an arc. And from here, I'm going to go more than halfway and make an arc. And what I'm going to end up with is this football thing. And I made mine so it reaches just about this vertex, which is okay, I guess. But if I made a mistake, it would be hard for me to tell. But if I did it correctly, then I expect that this angle and this angle are now congruent. In other words, I cut that angle exactly in half. I'm going to do it again to this one over here, but this time I'm going to do it consciously in a different way. There's my reference arc. And now this time I'm going to reset this so I get different endpoints than my vertex. And if I've done this correctly, what I would expect is that these two endpoints and my vertex would be 3 points that are collinear. And of course, we know that 3 points are not always collinear. They're only sometimes collinear. So only if I did this correctly would these 3 points end up in a straight line. And if I did it correctly, then I would expect these two angles to have been bisected. And if I do it to this third one, it'll give me a better sense of whether I made a mistake with the other ones. Because if I did it right, then they should all meet at one point. And if I didn't do it right, then they'll meet at some other spot. Or they won't meet at a single point. They'll be like a little triangle formed in the middle. So pretty darn close. There is a little triangle in there. I made a little mistake in my red one, I think. But again, these 3 special segments in a triangle, all angle bisectors, generally meet at a point of concurrency. And I now contend that this is the center of the triangle. Does this look more like the center of the triangle to you? But look how far away it is from over here versus how far away it is from here. Well, I think this is definitely a center of a triangle, and this particular center is more commonly viewed as a center because we're talking about the middle. And what it means is that if I just a little bit better. if I extend these so that it just touches each side, it is the center of a circle that just barely fits on the inside of this shape, inscribing a circle inside. So this is called the inscribed, the inscribed circle. Therefore, it's called the incenter. Incenter. And it's a different type of circle, center of the triangle. And then lastly, one more example. My eyes are getting tired after staring at the screen all day, and I can't see as well. So remember what we did with our perpendicular bisectors before, where we went more than halfway and made our little circles. Do that same thing again and leave it the same size at each time. That's all a compass does, is it keeps a consistent radius for our circles. And that's why when I asked you to buy one, that I asked you to buy one that was a bow compass that allows you to adjust it here rather than like pull it open. And this time, what I'm going to do is I actually don't care about the perpendicular nature of this. I only care about the bisector nature of it. Because what I want to do is take that midpoint of the side and I want to connect it to the opposite vertex. The same thing here. I'm going to take this, figure out where that intersection would be, and then I'm going to connect it to the opposite vertex. And these are called medians now. This is one of the terms on your sheet from last class. And if I do take all three of these medians, connecting that midpoint to the opposite vertex, they meet at a point of concurrency. And if I were to cut this out, like of cardboard, this would be the exact spot for me to place my pen on so that it would perfectly balance. It's the center of gravity. And no, it won't draw a circle on the inside, and no, it won't draw a circle on the outside. But do you remember the formula for the area of a triangle? 1/2 base times height. So this base has been split in half here, which means this part and this part are congruent. So this times the height divided by 2 gives you this area. And this same length times the same height divided by the same 2 gives you this area. So this region and this region have equal areas. And the same is true when I turn it this way and I look at this region versus this region. And the same is true when I look at it in terms of this region and this region. So by using these medians, what it gives me is this point where the weight is evenly distributed on all sides. And as a result, this is the center of gravity. This is the coolest name as well. This one is called the centroid. So there are multiple centers that we can use for these triangles, and that's what this unit is about today. We are going to talk about all the specialty things that can happen in triangles. And hopefully you've got the notes printed out or pulled up in Google. And to begin, while you get those things going, I'm going to tell you a little story. This is one of my favorite. Hold on, let me see a couple questions here. Should we be copying this? No. Does this only work with scalene triangles? No, it does not. Turns out, can you send the link? Turns out that in the event that you, hold on, let me get this link out to everybody. In the event that you do it with an equilateral triangle, the perfect triangle, all three of those centers, the incenter, the circumcenter, the centroid, and even a fourth one called the orthocenter, will all fall in the exact same point, because in an equilateral triangle, there is only one center. If you stretch that triangle a little bit, so it's now isosceles, what you'll find is that all those centers line up vertically. They all form in a line. And then once you start stretching it out in odd ways, they all spread out in their own directions. It's kind of cool. Okay, link, scaling triangles, copy this. Okay. So I want to tell you a little story about this one, triangle midsegments. About 25 years ago, I was racing sailboats in San Francisco Bay. That was my hobby. And I was chartering a boat. I didn't own the boat at first, and I wasn't great at it, but I did all right. I'm smart enough to figure some things out, and I learned from some seasoned masters, these 60-year-old guys who had been out on the water forever and knew the tide by the taste of the wind and things like that. And I was fortunate enough to get involved with this fleet called the Canars, Knarr. It's a Scandinavian fleet. And the San Francisco Bay had a fleet of about 25 or 30 boats that was really quite strong. And there was no other fleet in the United States. Denmark had a fleet in Copenhagen that was about the same strength. And Norway actually had two fleets, one in Oslo and one in Bergen. And they worked it out so that every year, the best sailors would compete in the International Canard Championships. And so I was able to go to each of those places at some point, but the one particular year I'm speaking of was in Norway. We went to Bergen, and we're going to race in the international championships. And the way they do it is they bring in, say they have 28 boats in Bergen. They will cut it in half and say, okay, so our 14 top sailors get to sail in the internationals, and then we'll get 7 from Denmark and 7 from the United States. And then they rotate boats throughout the week so that nobody has an advantage of a better boat and nobody gets their own boat. And you spend 3 days racing, and then you get a lay day where you get a chance to kind of experience the culture and go out and do some touristy stuff, and then 3 more days racing, and then the presentation of the Regatta Cup and all that kind of stuff. And so on the middle day, I decided to go check out the fjords of Norway. I don't know if you know much about fjords. I don't know the actual definition, but basically it's like these rivers that run through the mountains and these glaciers, and they're super deep, thousands of feet deep. And the water, because it's glacial all around you, is freezing cold, like jet black, and there's steam coming off of it to show you that it's, basically 31.9 degrees or something like that Fahrenheit. And the walls are super steep, and so no light gets in, and it's just dark and foreboding and really kind of creepy and cool. So I decided to take a tour through these things. And it was a ferry tour on boat, and the boat had to transfer me at some point along the way. So they gave me a ticket and said, transfer, and in the transfer section said Midfjorden. So being the kind of resourceful guy I am, I start looking around with all the maps, trying to find the town of Midfjorden where I'm going to be transferring. And I can't find it. There's all these little towns, and we'll come through this section of the really deep walls and caverns, and suddenly it'll open up, and there's this beautiful meadow with like 3 little kind of chalet Hansel and Gretel style houses there. And it's an entire town that lives in the middle of nowhere, and they have to take a boat to go anywhere and get anything. But it's beautiful. And as I'm going through here, I'm just wondering which of these little towns I get to stop in, and I get to, talk to the locals, and maybe they'll buy their little local food items or something like that. And it's just going to be this great experience. But I keep waiting and waiting and waiting, and I'm not finding anything that says Midfjorden. So I start asking people, and I say, can you tell me where Midfjorden is, please? And they look at me like I'm an idiot. Midfjorden is Midfjorden. Well, that doesn't help me. So I pull up a map, and I'm like, I'm looking on the map. Can you point to where Midfjorden is? Midfjorden is Midfjorden. And they're, no help whatsoever. And I'm kind of confused at this point. So eventually I hear the announcer come over, and he says, transfer Midfjorden. Okay, great. So I go over to the exit, and they open up the door, and I'm expecting to be like on this little plank going out onto this idyllic little township. And they're not. They're in the middle of the fjord, right? I can see the water down there, and they've got the gate open, and there's this waft, freezing cold air, and I shiver as I feel it. And I just see this sea of black, looks like molten glass just begging you. And I'm like, what, you want me to swim in or something? And they pull up another boat next to us, and they open up its door and they drop this 2x6 plank, and it's probably 8 feet away. And they just drop this plank across. Okay, transfer. And so I start walking across this thing, and I'm looking down, and the creak, right? I'm hearing the plank creak, and I feel the cold air working its way up the pant legs and kind of around my ankle, and I'm shivering again, and it hits me. Midfjorden means in the middle of the fjord. And that's why they were looking at me as such idiots, right? They're like, I can't tell you where the middle of the fjord is. These two boats are going to come together, and they're going to meet in the middle somewhere. And wherever they happen to cross, that's where we'll transfer the people, and then they'll continue on their way. So I use this story to explain that sometimes the name is exactly as you expect. For example, a triangle mid-segment is simply a segment that is in the middle of the triangle. But it's very specific in terms of how it's the middle. A triangle mid-segment is a segment connecting the midpoints of two sides of a triangle. So you can see that D here is a midpoint of this side because these segments are congruent. And E is a midpoint of this side because these segments are congruent. These two are not the same, right? This has 2 marks and this has 1 mark. But I know these are midpoints and they're connected to form a segment. Therefore, it's called a mid-segment. In this example, that mid-segment is the segment DE. And you remember we put the notation over the top to say it's a segment. Well, what good is a mid-segment? Well, it turns out that in addition to it being kind of just interesting running through the middle, it has 2 real features to it. If a segment joins the midpoint of 2 sides, then the segment is parallel to the 3rd side and exactly half as long. So this DE is going to be parallel to AC. And if this length is X, this length AC will be exactly twice as long, 2x. So using the diagram above, if DE is a mid-segment of ABC, then we can say that DE is parallel to AC. And we can say that DE as a length, I'm not using the segment on top now, is 1/2 the length of AC. We can now use that information to solve problems. Please forgive the notations here because I've cut and pasted, and so the numbers don't go in sequence. First, let's identify all pairs of parallel parts, or parallel segments. So what if I said WY? What segment would be parallel to that?
Segment QR.
Very good, segment QR. What if I said XW? What segment is parallel to XW? Looks like RS. And lastly, it looks like we've got XY, which would be parallel to QS. So the second piece is going to be, in addition to parallel, we've got this half length thing. So if we're told that F, G, and H are all midpoints, and we're told that the length FG is 9 units long, we can immediately make a conclusion about that. We know that this is a midpoint. Thus, since this is a midpoint, this is called a midsegment. And a midsegment is half the length of the side that it's parallel to. So in other words, how long must DE be? Twice as long, or 18. And that makes sense because this little segment here has been bisected by H, so that each of these parts will be 9. And then they tell us that GH is 7. So we know that the side that's parallel to that has 2 little parts that are 7. And therefore the whole length CE would be 14. And just to throw a little wrinkle your way, they say that CD is 24. What can we surmise from that?
FH is 12.
Good. This has to be half as big. Now, when you're looking to find the perimeter, of course, you just add the outer parts. We've written these out nice and smoothly, so it'd be very easy to say 24 plus 18 plus 14, 40, 52, 56 would be the perimeter. Without doing the math, would you like to guess what the perimeter of the inner mid-segment triangle is? Okay, well, let's do the math. 9 plus 12 is 21, and 7 is 28.
It's half of the perimeter of triangle CDE.
It is, isn't it? Because these are all mid-segments, they're half as much, and so they're going to be half the overall size. In other words, the perimeter of the mid-segment triangle is half the perimeter of the overall triangle. What about the area, though? Do you see how this triangle has a 7, a 9, and a 12 on it? And this triangle has a 7, a 9, and a 12 on it. And this triangle is a 7, 9, and 12. And this one's 7, 9, and half of that side, so 12. So in other words, this triangle was broken up into 4 congruent triangles, one of which is this mid-segment triangle. So the area of the overall triangle is not twice as big. The area is 4 times as big. We'll learn about this in about February when we talk about similar figures. But in concept, it's because if each of the side lengths is doubled and you multiply 2 side lengths to find area, then the area is quadrupled because it's 2 times 2. All right. So then let's come over here. Number 3 is asking the exact same information as this one. I'm going to leave that one for you guys to do yourself. Here's an application of it that's a little bit harder. Now what we're saying is we've got a mid-segment, but instead of having numbers on it, we have expressions, algebraic expressions. But the concept is the same. We know that this mid-segment is parallel to the base and half as long. Therefore, 6x plus 31 is half of 19x minus 36. I could distribute that 1/2, but that's going to give me some decimal values that make it difficult. So I'm going to choose to get rid of this half by multiplying everything through by 2. 12x plus 62 equals, the 2 will cancel that out, leave me with 19x minus 36. I'll subtract 12x and add 36. And I get 98 equals 7x. So x is 14. This time we didn't use the parallel nature, we just used the half length nature. Any questions on number 6, that is? As you're seeing, your homework tonight will be based on the problems that I've left for you to do. So I'm going to leave you these 2 problems to do. Let's do this one, though, to give you an example of this one. In this case, it's telling us that this segment, because these are midpoints, is a midsegment. And we know that the midsegment is what to the side it doesn't reach, doesn't touch. Parallel to it. Yes, thank you. Thank you. It is parallel to it. And if it's parallel, then we could draw a transversal. And that should spark some ideas in your head. If parallel, transversal, we can make some conclusions. So it looks like angle 2 is really easy to work with. What do we know about angle 2 and the angle marked as 127?
It's a linear pair.
Excellent. It's a linear pair. Linear pairs are supplementary. Therefore, I know that 127 plus the measure of angle 2 is equal to 180. So the measure of angle 2 must be 53. Easy peasy. What about angle 1?
It's also supplementary because they're same side interior.
Excellent. You can see that these are same side interior and thus do the same calculation. Or you could say that 1 and 2 are corresponding. And since you've already found 2, you know that 1 has to be the same. So 1 is also 53 degrees. Before we move on to 3, let's go to, what do you think? Which is easier, 4 or 5? Well, I know that 4 is corresponding if this is my transversal, and these are my parallel lines making my bridge. 4 and the angle marked as 59 are corresponding, so they're going to be congruent. So that's going to be 59 degrees. And once I get that, I know that 5 and 4 measure of angle 5 plus 59 equals 180. So the measure of angle 5 has to equal 121. What about angle 3?
Well, all angles in a triangle add to 180. So on the little one, you can add together angles 2, 4, and then you can find the number 3.
Excellent. I know that it makes triangles, and I could either use the big triangle or the little triangle. It's going to end up being 53 degrees plus 59 degrees plus the measure of angle 3 equals 180. So that's 112 plus the measure of angle 3 equals 180. So the measure of angle 3 is equal to 68 degrees. And we'll leave number 11 for you guys to do. Same type. Any questions? Page 2, talking about perpendicular bisectors. I want you to picture that this is like a tower that you're putting up, like a really tall something or other, and you're putting it into the dirt. And when you do that, you're going to make it go straight up and down, right? You're going to make it perpendicular, and you're a little worried it's going to fall over. So you go out and you put these stakes in the ground. Turns out, if you go out the same distance in both directions, and of course in a three-dimensional world, you could even go not in a straight line, but then you extend those up to touch some point on your tower, those two lengths of the guy wires would always be the same. How can we prove that? Well, do you agree that if this is a right angle, this must also be a right angle? They're a linear pair, they add up to 180, so if I subtract 90, what I'm left with is 90. Those both have to be right angles, they're congruent. I was told that these two lengths are the same, and I know by the reflexive property of congruence that this side is the same as itself, which means these two triangles are congruent by side, angle, side, side, angle, side. Therefore, by CP, CTC, I can say that any corresponding parts must also be congruent. So I know that these two sides will always be congruent. Now, what gets cool about this is that it turns out that any two of those three components, the guy wires being the same length, the angles being right, and these bases being the same length, if you have any two of those, the third one must also be present. If you have the right angle and the split here, these must be the same. If you have these being the same and a right angle here, then these will be split evenly. If you have these the same and these the same, then it'll be a right angle. So if they're perpendicular and AD is congruent to BC, then we know that AC equals BC. And conversely, I don't like the way they do this. I think this should be if CA and CB are congruent, instead of then there, this should be and CD is perpendicular to AB, and this one becomes then these are the same. AD equals BD. It's a cool concept, and I can see using this in putting up tent stakes and things like that. But the math and the algebra and the application of it is really boring. Let's say that you knew algebra, but you had no idea about geometry. What would you want to do with these two expressions? set them equal to each other and solve, right? That would be your natural inclination, which is exactly what we're going to do for all of these. You're not going to get much out of that process, honestly, but this is the way you're going to see problems come forth. Subtract, add, and so we're going to get 60, 72 equals 6x, x equals 12. All these are going to be exactly that. You'll set them equal to each other. But what I ask you to do is instead look at them and say, in this case, I have the guy wires being congruent and perpendicular. That means this bottom is bisected. Here I've got the bottom being bisected and a right angle, therefore the guy wires are the same length, right? Try to think about the different pieces, because if you have any two, the third must follow. Any questions on the perpendicular bisector theorems? Okay, I'll leave those three for you to solve. Then we've got the angle bisector theorem. You guys know the movie The Black Panther? And you know that scene with the train running between like those magnetic little buffer things, where it's running right down the middle? This totally reminds me of that. What this says is that if you've got an angle and you come shooting out of it in a way that exactly splits that angle in half, the little magnetic things on these walls are going to keep it always in the middle. It's always going to be exactly in the center. So if you were to measure from here, perpendicular to the side, that length would be the same as here, perpendicular to the side, that length. No matter where you pick along there. If it's an angle bisector, then the distances here will be consistent. And you might remember back in Unit 3 when I made you figure out how to find the distance between a point and a point on the line, or the distance between the point and the line. You had to figure out the perpendicular, and then you had to find the point of intersection, and then you took a really long process. The point of that was to get you thinking that when you look at a distance between a point and a line, you're always looking for that perpendicular distance. That's what the shortest distance is. So they're kind of being redundant here. They're making it part of the given. If AD bisects angle BAC and these are perpendicular, then you know that BD is equal to CD. Those parts will be the same length. And it does work the other way as well. If you turn on those little magnetic things that trap the train in the middle and you fire it towards that angle, when it hits the angle, it'll be a perfect angle bisector. It'll be right in the middle. Then AD bisects angle BAC. And again, even though the concept is cooler than some of the other stuff, the application is going to look pretty boring. It's just going to say, okay, here I've got the angle bisector. These are perpendicular. Therefore, those lengths will be the same. 4x plus 30 equals 9x minus 5. Subtract, add 35 equals 5x. X equals 7. Not a lot of intrigue there. Any questions on the angle bisector theorems? Okay. Last piece are those two centers that we talked about at the beginning when I was doing the constructions for you. First one is called the circumcenter. And if the perpendicular bisectors of the sides of a triangle, then the perpendicular bisectors of the sides of a triangle intersect at a point called the circumcenter. The circumcenter is always equidistant from the vertices of the triangle. In other words, this was that one that I did here, where we found the perpendicular bisectors, and that center, people didn't want to call it a center, but once I drew it through the vertices, you had a better sense of understanding this is one of the versions of the centers. And I like to think about this as a theorem, actually. If you construct the perpendicular bisectors, finding the circumcenter, then the circumcenter will be equidistant from the vertices. This picture is a very similar picture, what you're going to see like in SATs and in whatever. It comes up a lot, and I think it's super confusing. What they're trying to do is convey a couple of things. The hypothesis is presented by saying this is a perpendicular bisector. You can tell because it's bisecting the side and it's perpendicular. You might want to continue it on here, but don't. You might be tempted to say it also goes up here through the point A, but we don't know that. Just like through here, we can see that this perpendicular bisector definitely does not go up through B, does it? It goes straight up. It would be different. And in fact, even though this one looks almost like a straight line, and I know we said that that's the one thing we'll never fool you on, I think this one tends to try to fool you that way. But all those orange lines are perpendicular bisectors. So when it says list the perpendicular bisectors, PE is 1, PF is 1, PD is 1. And if those are 3 perpendicular bisectors, as we said, they all have a point of concurrence, and they all meet at one point. And since they've all got a P in them, we know that that point is P. That's our circumcenter. Once we've identified the circumcenter, we can then use it to say the conclusion part here, which is that it's always the same distance from the vertices. So this length here will be the same, 4, I guess, as this length here is the same as this length here. So AP would be congruent to CP, which would be congruent to BP. And they're trying to convey all that in one picture, and I think it comes out confusing. But let's try to apply it here. They tell us Z is the circumcenter. And I'll tell you that I'm going to contact the worksheet maker of this and tell them that they really need to put perpendicular marks here. Because otherwise these could be going off in crazy directions and you wouldn't know that they're bisecting the sides. But if we're trying to find TU, and we know that this part is 19, and that it is the circumcenter, we know that the only way a circumcenter can be formed is if these perpendicular bisectors meet there. So that means that this piece has to be the result of a bisector. If that's 19, that's 19, which means TU equals 19 plus 19 equals 38. And then they want VY. Okay, that's kind of the same idea, isn't it? If this is coming down perpendicular from a circumcenter, then it has to be the bisector. So whatever length this is has to be the same as this one. So if this is X, this is also X. So VY equals X. Well, let's go VY arrow. X plus X equals 34. So 2X equals 34. So X equals 17. VY is 17. A big colon. That was weird. All right, what about UZ? Is this hypothesis or conclusion? The hypothesis says if they have perpendicular bisectors meeting, and the conclusion says then it's equidistant from the vertices. This is conclusion. This is saying how far is it to this vertex? And they give you that it's 21 to this vertex. So shouldn't it be the same? because VZ should be the same as UZ, should be the same as TZ. In this case, that would be 21. So UZ would be 21. And again, I'm not a huge fan of this because I don't think we've really done this before. I haven't proven it to you. What they're saying is if this is 15 and this is a right angle and this is 21, how could you find X? And I know you've learned this, but I haven't proven it to you. Therefore, I'm hesitant to use it. But the book does. What's the relationship between three sides in a right triangle? Some guy named Pythagoras made his name on this. A squared.
A squared plus B squared equals C squared.
Thank you. So I'd say that X squared plus 15 squared equals 21 squared. So X squared plus 225 equals 441. So X squared equals 216. So X equals square root of 216. Now at this point, I would be okay with that as your solution. Soon enough, I'll teach you how to factor that and reduce that. The way to do that is to factor this down. 216 is divisible by 454. So it's 2 times 2. 54 is 2 times 3 times 3 times 3. And if I factor that into its prime numbers, what I'm looking for is numbers that can come out as a matched pair. These other ones are stuck on the inside, and that tells me that this is 6 square root of 6. And again, you're not responsible for that yet. That'll be in about March. But if we know that this part is 6 root 6, and we know that this was a bisector, that's also 6 root 6. So how long is TV? Well, if one of them is 6 of the root 6, another one is another 6 of the root 6, then together they make 12 of the root 6s. Okay. Last one, the incenter. This is the other one that I constructed for you. The angle bisectors of the angles of a triangle intersect at a point called the incenter. And the incenter is always equidistant from the sides of the triangle. This is the one that draws the triangle on the circle on the inside. So this time they're doing it differently. They're saying, okay, first we have the hypothesis is the angle bisectors. AP, CP, BP. The incenter is the common point again, which is P. And the listing of the congruent segments is the conclusion. If these are angle bisectors, then all these little distances to the sides are the same. So we'd expect that PD is congruent to PE is congruent to PF.